Was there advanced civilizations before humans? A comprehensive examination of pre-human intelligence and the search for lost civilizations. The question of whether advanced civilizations existed before humans captures our imagination and challenges our understanding of life on Earth. While Hollywood has popularized ideas of ancient alien visitors and lost technological societies, the scientific reality is far more nuanced and equally fascinating. This examination explores what we know about intelligence before humans, the evidence we would expect to find from advanced civilizations, and the tantalizing possibilities that emerge from recent discoveries in paleontology, archaeology, and astrobiology. When we speak of advanced civilizations, we must first define our terms. What constitutes advancement? Is it tool use, language, social organization, technology, or something else entirely? And what do we mean by before humans? The human lineage stretches back millions of years, with our species, Homo sapiens, emerging around 300 years ago. But intelligence, in various forms, has been evolving on Earth for hundreds of millions of years. The search for pre-human civilizations is not merely an academic exercise. Understanding the development and potential limits of intelligence on Earth provides crucial insights for astrobiology, the search for extraterrestrial intelligence, and our own future as a technological species. It forces us to confront fundamental questions about the nature of intelligence, the inevitability of technological development, and the long-term survival prospects of advanced civilizations, the timeline of intelligence on Earth. To understand the possibility of pre-human civilizations, we must first examine the timeline of intelligence on our planet. Earth formed approximately 4.6 billion years ago, with the first signs of life appearing around 3.8 billion years ago. For most of Earth's history, life consisted of simple, single-celled organisms. The emergence of complex multicellular life, known as the Cambrian explosion, occurred around 540 million years ago. The first nervous systems appeared in simple animals like cnidarians, jellyfish, and corals over 600 million years ago. These primitive neural networks allowed basic responses to stimuli, but were far from what we would consider intelligence. The development of centralized nervous systems and brains occurred gradually over hundreds of millions of years. Fish, the first vertebrates, appeared around 500 million years ago, followed by amphibians around 365 million years ago. Reptiles emerged around 320 million years ago, with dinosaurs appearing approximately 230 million years ago. Mammals evolved around 200 million years ago, initially as small, nocturnal creatures living alongside the dinosaurs. The mass extinction event that ended the Mesozoic era 66 million years ago eliminated non-avian dinosaurs and opened ecological niches for mammals to diversify. Primates appeared around 55 million years ago, with the human lineage diverging from other apes approximately 7 million years ago. This timeline reveals several crucial points. First, complex nervous systems capable of sophisticated behavior have existed for hundreds of millions of years. Second, various groups of animals have independently evolved high levels of intelligence multiple times throughout Earth's history. Third, the vast majority of Earth's history occurred before humans or even human ancestors existed. Evidence for ancient intelligence. When examining the fossil record for evidence of pre-human intelligence, we must look beyond brain size and consider behavioral indicators. Tool use, social organization, problem-solving abilities, and environmental manipulation all provide clues about cognitive capabilities. The most compelling evidence for ancient intelligence comes from dinosaurs, particularly theropods. Recent discoveries have revealed that many theropod dinosaurs exhibited complex behaviors previously thought to be unique to mammals and birds. Fossil evidence shows that some species built elaborate nests, engaged in sophisticated parental care, and lived in complex social groups. Troodon, a small theropod that lived around 75 million years ago, possessed one of the largest brain-to-body ratios of any dinosaur. Its brain structure, inferred from skull casts, suggests capabilities for complex problem-solving, and possibly even rudimentary reasoning. Some paleontologists speculate that if the mass extinction event hadn't occurred, Troodon or similar species might have continued evolving toward even greater intelligence. The discovery of dinosaur tracks, showing coordinated group movement, evidence of pack-hunting behavior, and fossils of dinosaurs engaged in complex social interactions all point to cognitive abilities that were previously underestimated. Some species appear to have used tools, such as stones for cracking eggs, or sticks for extracting insects. Marine reptiles of the Mesozoic also showed signs of advanced intelligence. Plesiosaurs and mosasaurs exhibited complex hunting strategies and social behaviors. The large brains of some marine reptiles suggest cognitive capabilities that may have rivaled those of modern marine mammals. Even earlier, during the Permian period around 250 million years ago, some therapsids, mammal-like reptiles, showed evidence of complex social behaviors and possibly even primitive tool use. These creatures were the ancestors of mammals and may have possessed cognitive abilities that were lost during the mass extinction events that followed. The Silurian Hypothesis. One of the most intriguing scientific concepts related to pre-human civilizations is the Silurian Hypothesis, proposed by astrophysicist Gavin Schmidt and astrobiologist Adam Frank in 2018. Named after the fictional reptilian species from Doctor Who, this hypothesis explores what evidence we might expect to find if an industrial civilization had existed on Earth millions of years ago. The Silurian Hypothesis doesn't argue that such civilizations existed, but rather examines what traces they would leave, and how long those traces might persist in the geological and fossil records. This thought experiment reveals surprising insights about the detectability of ancient civilizations and the assumptions we make about technological development. According to Schmidt and Frank's analysis, an industrial civilization that existed for even several thousand years might leave remarkably little trace in the geological record if it occurred millions of years ago. Most human-made materials would decay, erode, or be recycled by geological processes. Even our cities and monuments would likely disappear within a few million years. However, certain signatures might persist. These could include unusual isotopic ratios in sedimentary rocks, particularly carbon isotopes that might indicate large-scale fossil fuel burning. Elevated levels of certain metals or rare earth elements could suggest large-scale mining and processing. Plastic particles might persist in certain geological formations, and nuclear waste could leave distinctive isotopic signatures. The hypothesis also considers the rapid changes in atmospheric chemistry that an industrial civilization might cause. Elevated carbon dioxide levels, changes in nitrogen cycling, and other atmospheric modifications could be preserved in ice cores, tree rings, or sedimentary deposits, depending on the time scale and preservation conditions. Importantly, the Silurian Hypothesis highlights how brief most industrial civilizations might appear in the geological record. Human industrial civilization is only about 200 years old, and even if we persist for thousands of years, this would represent an incredibly brief moment in geological time. An alien geologist studying Earth millions of years from now might struggle to detect evidence of our existence. Alternative evolution paths. The evolution of intelligence on Earth has followed a particular path, but this doesn't mean it was the only possible path. Throughout Earth's history, various evolutionary pressures and opportunities might have led to different outcomes, potentially including the development of technological civilizations by non-human species. Consider the cephalopods, which include octopuses, squid, and cuttlefish. These marine invertebrates have evolved remarkable intelligence independently from vertebrates. Octopuses demonstrate problem-solving abilities, tool use, and complex behaviors that rival those of many vertebrates. They have sophisticated nervous systems with hundreds of millions of neurons distributed throughout their bodies in ways that differ fundamentally from vertebrate brain organization. The intelligence of cephalopods raises intriguing questions about alternative evolutionary paths. If cephalopods had evolved under different conditions, perhaps with longer lifespans or greater social cooperation, might they have developed more advanced technologies? Their ability to manipulate their environment, combined with their problem-solving skills, suggests that alternative forms of intelligence and technology might be possible. Marine mammals present another fascinating case study. Dolphins and whales have evolved large, complex brains and demonstrate sophisticated social behaviors, communication systems, and problem-solving abilities. Some researchers argue that cetacean intelligence might be fundamentally different from human intelligence, adapted for a three-dimensional aquatic environment rather than terrestrial tool manipulation. The social insects represent yet another path toward collective intelligence. While individual ants or bees might not demonstrate high intelligence, their colonies exhibit emergent behaviors that solve complex problems through distributed decision-making. Some scientists speculate about whether insect colonies might represent a form of intelligence that we simply don't recognize as such. Throughout the Mesozoic era, various dinosaur lineages showed trends toward increasing brain size and behavioral complexity. The troodontids, dromaeosaurids, and ornithomimids all exhibited cognitive abilities that were advancing rapidly in evolutionary terms. If the mass extinction event hadn't interrupted this trajectory, some paleontologists speculate that dinosaur intelligence might have continued evolving toward technological capabilities. Even more speculatively, some researchers have suggested that certain plant networks might represent forms of distributed intelligence. Mycorrhizal networks, which connect trees and other plants through fungal partnerships, facilitate complex chemical communications and resource sharing. While this is far from human-like intelligence, it demonstrates that information processing and decision-making can occur in ways that we're only beginning to understand. The fossil record and its limitations. Understanding the limitations of the fossil record is crucial when evaluating the possibility of ancient civilizations. Fossilization is an extremely rare process, requiring specific conditions of burial, chemistry, and time. The vast majority of organisms that have lived on Earth left no fossil trace whatsoever. Soft tissues, which include brains and nervous systems, almost never fossilize. Our understanding of ancient intelligence relies primarily on indirect evidence, such as skull casts, trackways, nest sites, and tool marks. This means that behavioral complexity and cognitive abilities could be significantly underrepresented in the fossil record. The temporal resolution of the fossil record also presents challenges. Even in the best preserved sequences, individual fossil layers typically represent thousands to millions of years. A civilization that existed for only a few thousand years might be compressed into what appears to be an instantaneous event in geological terms, making it extremely difficult to detect or study. Geographic sampling bias further limits our understanding. Fossil preservation is more likely in certain environments, such as riverbeds, lake bottoms, and marine settings. Terrestrial environments, where intelligent species might be most likely to develop technology, are often poorly represented in the fossil record. The search for technological artifacts in ancient rocks faces additional challenges. Most materials used by early human civilizations, such as wood, bone, and stone, would not survive millions of years. Even metals would likely oxidize and disperse. Only under very specific conditions might technological artifacts be preserved over geological timescales. However, some researchers are developing new approaches to searching for ancient technological signatures. These include looking for unusual isotopic ratios that might indicate large-scale processing of materials, searching for microscopic artifacts in sedimentary rocks, and examining chemical signatures in ancient soils that might indicate agriculture or industrial processes. Recent advances in analyzing microscopic fossils and chemical traces in rocks have revealed new insights about ancient life. These techniques might eventually be applied to searching for evidence of ancient intelligence or technology, though such searches have not yet yielded compelling results. Precursors to human intelligence. The evolution of intelligence in the human lineage provides important insights into how advanced cognitive abilities develop over time. Understanding this process helps us evaluate whether similar developments might have occurred in other lineages throughout Earth's history. The earliest members of the human lineage, such as Australopithecus, already showed signs of advanced intelligence compared to other apes. Tool use, which was once thought to be uniquely human, is now known to occur in many species, including several of our early ancestors. Australopithecus africanus, living around 3 million years ago, may have used bone tools for digging and processing food. The genus Homo, which includes our own species, emerged around 2.8 million years ago. Early Homo species like Homo habilis demonstrated increasingly sophisticated tool-making abilities, creating the first stone tools and showing evidence of planning and foresight in their construction. Homo erectus, living from about 2 million to 300,000 years ago, represents a major leap in cognitive development. These early humans controlled fire, created standardized tool designs, and spread across much of Africa and Asia. Their ability to adapt to diverse environments and maintain complex technologies across generations indicates advanced cognitive abilities. The Neanderthals, our closest extinct relatives, possessed sophisticated technologies, created art, and demonstrated complex social behaviors. Recent discoveries have revealed that Neanderthals made jewelry, used pigments for body decoration, and possibly had symbolic communication systems. Their brain sizes were actually larger than those of modern humans, though organized differently. The emergence of our own species, Homo sapiens, around 300,000 years ago, was followed by what archaeologists call the Great Leap Forward, or the Upper Paleolithic Revolution around 50,000 years ago. This period saw an explosion of technological and cultural innovations, including advanced stone tools, art, music, and sophisticated hunting strategies. This evolutionary trajectory raises important questions about intelligence in other lineages. The development of human intelligence involved multiple factors, including bipedalism, tool use, social cooperation, language, and environmental pressures. Different combinations of these factors might have led to different forms of intelligence in other species. Some researchers argue that human intelligence is the result of a rare combination of circumstances that is unlikely to be repeated. Others suggest that given sufficient time and appropriate selection pressures, various species might develop technological capabilities. The rapid evolution of intelligence in the human lineage, occurring over just a few million years, suggests that under the right conditions, advanced cognition can develop relatively quickly in evolutionary terms. Evidence from deep time. When searching for evidence of ancient civilizations, researchers must consider traces that might persist over millions or even billions of years. These deep time signatures would be fundamentally different from the archaeological evidence of recent human activity. One of the most promising areas of research involves examining unusual chemical signatures in ancient rocks. Large-scale industrial activity would likely leave distinctive isotopic ratios in sedimentary deposits. For example, the burning of fossil fuels produces characteristic carbon isotope signatures that differ from natural biological processes. Similarly, large-scale metal processing would leave traces of unusual element concentrations. The Anthropocene, our current geological epoch, is characterized by distinctive chemical and biological signatures that result from human activity. These include elevated atmospheric carbon dioxide, widespread distribution of plastic particles, altered nitrogen cycling, and the global distribution of radionuclides from nuclear testing. An ancient civilization might have left similar but different signatures in the geological record. Some researchers have proposed looking for ancient nuclear waste signatures. Nuclear materials have extremely long half-lives and could potentially be detected millions of years after their creation. However, natural nuclear reactions, such as those that occurred at Oklo in Gabon around 2 billion years ago, demonstrate that not all nuclear signatures indicate artificial origin. The search for ancient megastructures presents another avenue of investigation. Large-scale engineering projects might leave traces detectable in the geological record. However, most surface structures would be eroded away over millions of years, and even underground installations would likely be altered by geological processes. Paleontologists have occasionally discovered anomalous fossils or geological formations that some have interpreted as possible evidence of ancient intelligence. However, closer examination has invariably revealed natural explanations for these phenomena. The tendency to see patterns in intelligence where none exists, known as pareidolia, makes it crucial to apply rigorous scientific standards to such claims. Recent discoveries in astrobiology and exoplanet research have provided new perspectives on the search for ancient intelligence. The detection of potentially habitable exoplanets and the study of extremophile organisms on Earth have expanded our understanding of where and how life might evolve. These insights inform our search for ancient intelligence on Earth by highlighting the diverse forms that life and intelligence might take. The Drake equation applied to Earth. The famous Drake equation, formulated by astronomer Frank Drake in 1961, attempts to estimate the number of communicating extraterrestrial civilizations in our galaxy. Interestingly, this equation can be modified and applied to estimate the likelihood of advanced civilizations having existed on Earth before humans. The terrestrial version of the Drake equation would consider factors such as the rate of evolution of complex life on Earth, the fraction of complex life that develops intelligence, the fraction of intelligent life that develops technology, and the length of time such civilizations persist. Applied to Earth's 4.6 billion year history, this approach provides a framework for evaluating the probability of pre-human civilizations. Several factors favor the possibility of ancient Earth civilizations. The enormous timescales involved mean that even if the Great Filter concept, proposed by economist Robin Hanson, suggests that there are extremely difficult evolutionary steps that prevent most life from developing into spacefaring civilizations. If the Great Filter lies behind us, it might explain why we don't see evidence of ancient Earth civilizations. Alternatively, if the Great Filter lies ahead of us, it might suggest that technological civilizations tend to be short-lived, making their detection in the geological record unlikely. The Fermi paradox, which questions why we haven't detected evidence of extraterrestrial civilizations despite the high probability of their existence, can also be applied to ancient Earth civilizations. If technological civilizations had existed on Earth for millions of years, we might expect to find more obvious evidence of their presence. Technological signatures in the geological record. Advanced civilizations would likely leave distinctive technological signatures that could potentially be detected millions of years later. Understanding what these signatures might look like is crucial for evaluating claims of ancient civilizations and developing methods to search for them. Industrial activity produces characteristic chemical signatures that differ from natural processes. Large-scale metal extraction and processing would concentrate certain elements in ways that don't occur naturally. The smelting of ores produces specific isotopic ratios that could potentially be preserved in sedimentary deposits. Energy production would also leave distinctive traces. The burning of fossil fuels produces carbon dioxide with specific isotopic compositions. Nuclear energy would create radioactive isotopes that might persist for millions of years. Even renewable energy technologies would require large-scale mining and processing of materials, leaving chemical signatures. Agricultural activities would alter the landscape and soil chemistry in ways that might be detectable over long timescales. Large-scale farming would change erosion patterns, alter the distribution of organic matter, and potentially introduce non-native species whose fossil remains might be found far from their natural ranges. Urban development would create distinctive geological formations. Cities concentrate materials in unusual ways, creating artificial sedimentary deposits that differ from natural formations. Even after the structures themselves have eroded away, these unusual deposits might persist in the geological record. Transportation networks would leave traces in the form of altered topography, unusual material distributions, and possibly even fossilized infrastructure under specific preservation conditions. Roads, tunnels, and other transportation infrastructure modify the landscape in ways that might be detectable millions of years later. Waste products from advanced civilizations would create distinctive signatures. Plastics, synthetic chemicals, and other artificial materials would leave chemical traces that differ from anything produced by natural processes. Even if the materials themselves don't survive, their breakdown products might be detectable. However, the detectability of these signatures depends heavily on preservation conditions and the scale of the civilization. A brief technological civilization that didn't significantly alter global biogeochemical cycles might leave very little trace in the geological record. The key question is whether any ancient civilization could have reached sufficient scale and duration to leave detectable signatures while somehow avoiding detection by modern science. Alternative biochemistries and silicon-based life. While most discussions of ancient intelligence focus on carbon-based life similar to what we know today, some researchers have speculated about alternative biochemistries that might have supported different forms of intelligence in Earth's past, or might exist elsewhere in the universe. Silicon-based life has long been a staple of science fiction, and some scientists have seriously considered its possibilities. Silicon can form complex molecules similar to carbon, and under certain conditions, silicon-based biochemistry might be viable. However, silicon compounds are generally less stable and less diverse than carbon compounds under Earth-like conditions. During certain periods of Earth's history, conditions might have been more favorable for alternative biochemistries. The early Earth had a very different atmospheric composition. Little oxygen and high concentrations of methane, ammonia, and other compounds. Some researchers speculate that alternative forms of life might have evolved during these periods. The deep subsurface of Earth harbors unusual microbial communities that derive energy from chemical processes rather than sunlight. These extremophile organisms demonstrate that life can exist under conditions very different from those at Earth's surface. Some researchers speculate that more complex alternative biochemistries might exist in these deep environments. The concept of shadow biospheres suggests that alternative forms of life might exist on Earth alongside conventional life, using different biochemistries or genetic codes. If such shadow biospheres exist, they might represent evolutionary lineages that diverged from conventional life billions of years ago. While no convincing evidence for shadow biospheres has been found, the possibility remains intriguing. Mineral-based life represents another speculative possibility. Some researchers have proposed that certain minerals might be capable of self-replication and evolution under specific conditions. Clay minerals, for example, contemplate the formation of similar structures and might represent a primitive form of mineral-based life. While this is highly speculative, it raises questions about the boundaries between living and non-living systems. The study of extremophile organisms has revealed that life can exist under much more varied conditions than previously thought. Organisms have been found thriving in environments with extreme temperatures, pressures, acidity, alkalinity, and radiation levels. This expands the range of conditions under which intelligence might potentially evolve. The role of mass extinctions. Earth's history has been punctuated by several major mass extinction events that have dramatically altered the course of evolution. These events, while devastating, have also created opportunities for new forms of life to evolve and potentially develop intelligence. Understanding the role of mass extinctions is crucial for evaluating the possibility of pre-human civilizations. The most famous mass extinction occurred 66 million years ago at the end of the Cretaceous period, eliminating non-avian dinosaurs and many other species. This event opened ecological niches that allowed mammals to diversify and eventually give rise to primates and humans. Without this extinction event, dinosaurs might have continued to dominate terrestrial ecosystems, potentially preventing the evolution of large-brained mammals. However, this raises an intriguing question. What if dinosaurs had continued evolving for another 66 million years? Some paleontologists speculate that certain dinosaur lineages were showing trends toward increasing intelligence. The troodontids, in particular, had relatively large brains and sophisticated behaviors. Given sufficient time, might some dinosaur species have developed technological capabilities? The end Permian extinction, which occurred around 252 million years ago, was even more severe than the end Cretaceous event, eliminating over 90% of marine species and 70% of terrestrial species. This event reset the evolutionary clock and allowed entirely new groups of organisms to diversify. The survivors of this extinction gave rise to the dinosaurs, mammals, and many other groups that would dominate later ecosystems. Earlier mass extinctions also played crucial roles in shaping the evolution of life. The late Ordovician extinction around 445 million years ago primarily affected marine life, while the late Devonian extinction around 375 million years ago had major impacts on fish and early terrestrial ecosystems. Each of these events created new evolutionary opportunities and might have influenced the development of intelligence in various lineages. The pattern of mass extinctions and recoveries suggests that intelligence might evolve repeatedly throughout Earth's history, only to be cut short by catastrophic events. This could explain why we don't see evidence of ancient technological civilizations. They might have been eliminated by mass extinctions before leaving detectable traces in the geological record. Alternatively, mass extinctions might actually favor the evolution of intelligence by creating selective pressures for adaptability and problem-solving abilities. Species that can rapidly adapt to changing conditions and develop new survival strategies would be more likely to survive mass extinction events. This could accelerate the evolution of intelligence in surviving lineages. The recovery periods following mass extinctions are often characterized by rapid evolutionary innovation and the appearance of new. The vast majority of Earth's biosphere is aquatic, and the oceans have harbored complex life for hundreds of millions of years longer than terrestrial environments. This raises important questions about the possibility of advanced intelligence evolving in marine environments and whether aquatic civilizations might have existed before humans. Ecological strategies. These periods might be particularly favorable for the evolution of intelligence, as they provide opportunities for species to exploit new niches and develop novel behaviors. Marine intelligence and aquatic civilizations. Marine environments present both opportunities and challenges for the evolution of intelligence. The three-dimensional nature of aquatic habitats allows for complex spatial navigation and might favor the evolution of sophisticated cognitive mapping abilities. The acoustic properties of water enable long-distance communication, which could support complex social structures and cultural transmission. Many marine animals demonstrate remarkable intelligence. Dolphins and whales have evolved large, complex brains and exhibit sophisticated behaviors including tool use, cultural transmission, and complex communication systems. Some researchers argue that cetacean intelligence might be fundamentally different from human intelligence, adapted for a three-dimensional aquatic environment rather than terrestrial manipulation of objects. Cephalopods represent another pinnacle of marine intelligence. Octopuses, despite having evolved intelligence independently from vertebrates, demonstrate problem-solving abilities, tool use, and complex behaviors that rival those of many vertebrates. Their distributed nervous systems and camouflage abilities represent cognitive strategies that differ fundamentally from vertebrate intelligence. The challenge for aquatic intelligence lies in developing technology. Fire, which was crucial for human technological development, is impossible underwater. Metallurgy, ceramics, and many other foundational technologies require high temperatures that are difficult to achieve in aquatic environments. This suggests that aquatic civilizations, if they existed, would need to develop along very different technological paths. However, some researchers have speculated about alternative technologies that might be developed by aquatic species. Biotechnology, using living organisms as tools, might be more feasible in aquatic environments. The cultivation and genetic modification of other species for specific purposes could potentially lead to sophisticated biological technologies. Acoustic technologies might also be more developed in aquatic civilizations. The ability to manipulate sound waves for communication, navigation, and environmental sensing could lead to sophisticated acoustic technologies that have no terrestrial equivalent. Sonar-based technologies might be developed to levels far beyond current human capabilities. Architecture in aquatic environments might focus on the manipulation of currents, the cultivation of coral reefs or other biological structures, and the creation of three-dimensional living spaces that take advantage of the buoyancy provided by water. Such structures might be less likely to fossilize than terrestrial buildings, making them difficult to detect in the geological record. The vast majority of the ocean floor remains unexplored, and deep-sea environments might harbor evidence of ancient intelligence that has yet to be discovered. The preservation conditions in deep ocean sediments might be more favorable for maintaining traces of ancient activity than terrestrial environments. Quantum and information-based approaches. Recent advances in quantum biology and information theory have opened new perspectives on intelligence and consciousness that might be relevant to the search for ancient civilizations. These approaches suggest that intelligence might be based on physical processes that we're only beginning to understand. Quantum effects appear to play important roles in biological processes, including photosynthesis, avian navigation, and possibly even consciousness. Some researchers speculate that quantum processes might be fundamental to intelligence, and that advanced civilizations might have developed technologies based on quantum mechanics millions of years before humans discovered these principios. Information theory provides another lens through which to examine intelligence and civilization. Intelligence can be viewed as a process of information gathering, processing, and storage. Advanced civilizations would be characterized by their ability to manipulate information in sophisticated ways. This perspective suggests that we might search for ancient civilizations by looking for unusual information processing signatures in the geological record. The concept of computational archaeology proposes using advanced computing techniques to search for patterns in geological and paleontological data that might indicate ancient intelligence. Machine learning algorithms might be able to detect subtle patterns in rock formations, fossil distributions, or chemical signatures that would be invisible to human researchers. Some researchers have proposed that consciousness and intelligence might be fundamental properties of matter, similar to mass or electric charge. This panpsychist perspective suggests that intelligence might emerge naturally from complex information processing systems, and that various forms of intelligence might be more common in the universe than traditionally assumed. The idea of digital physics proposes that the universe itself might be a vast computational system. If this is true, then intelligence and civilization might be viewed as emergent properties of this underlying computational substrate. This perspective might help explain how intelligence could evolve repeatedly, and might suggest new ways to search for evidence of ancient intelligence. Quantum archaeology is a speculative field that proposes using quantum mechanical principles to retrieve information about past events from quantum traces in the present. While highly speculative, this approach might eventually provide new tools for investigating ancient intelligence and civilizations. The search for technosignatures, the search for extraterrestrial intelligence, SETI, has developed sophisticated methods for detecting technological signatures of advanced civilizations. These same techniques, adapted for terrestrial use, might be applicable to searching for evidence of ancient Earth civilizations. Traditional SETI searches focus on radio signals, but more recent approaches consider a broader range of technosignatures, including unusual atmospheric compositions, artificial structures, and industrial waste heat. Applied to Earth's history, we might search for ancient technosignatures in the geological and paleontological records. Atmospheric signatures represent one of the most promising approaches. Advanced civilizations would likely alter their planet's atmospheric composition through industrial activity, energy production, and waste disposal. These changes might be preserved in ice cores, tree rings, or sedimentary deposits, depending on the timescale and preservation conditions. The search for artificial structures in the geological record presents significant challenges, as most materials would not survive over millions of years. However, certain structures might leave lasting traces. Large-scale mining operations would alter the distribution of minerals in ways that might be detectable. Underground installations might be preserved under specific geological conditions. Isotopic signatures provide another avenue for searching for ancient technosignatures. Industrial processes often produce characteristic isotopic ratios that differ from natural processes. Nuclear technologies would create distinctive radioactive isotopes. Even chemical industries would leave traces in the form of unusual molecular distributions. The concept of planetary-scale engineering raises questions about whether ancient civilizations might have attempted to modify Earth's environment on a global scale. Such modifications might leave traces detectable billions of years later. However, the absence of obvious large-scale modifications suggests that if ancient civilizations existed, they either didn't reach planetary engineering capabilities, or their modifications have been erased by subsequent geological processes. Recent advances in astrobiology have identified potential biosignatures that might indicate the presence of life on exoplanets. Similar techniques might be applied to searching for ancient biosignatures on Earth that could indicate unusual or artificially modified biological systems. Implications for SETI and astrobiology. The search for ancient Earth civilizations has important implications for the broader search for extraterrestrial intelligence and our understanding of life in the universe. If advanced civilizations existed on Earth before humans, it would suggest that intelligence might be more common in the universe than currently assumed. The rare Earth hypothesis proposes that the combination of factors that allowed complex life to evolve on Earth is extremely uncommon in the universe. This hypothesis suggests that while simple life might be common, complex multicellular life and intelligence are extremely rare. Evidence for multiple independent origins of intelligence on Earth would challenge this hypothesis. Conversely, if no evidence for ancient Earth civilizations is found, despite thorough searching, it might support the idea that the evolution of technological intelligence is extremely rare and depends on a very specific set of circumstances. This would have implications for the likelihood of finding extraterrestrial intelligence. The longevity of civilizations is a crucial factor in both SETI and the search for ancient Earth civilizations. If technological civilizations tend to be short-lived, they would be extremely difficult to detect either in space or in Earth's geological record. The apparent absence of ancient Earth civilizations might indicate that technological civilizations have brief lifespans. The study of extremophile organisms and alternative biochemistries informs our understanding of where life might exist elsewhere in the universe. If intelligence can evolve in Earth's extreme environments or using alternative biochemistries, it expands the range of potentially habitable worlds and the forms that extraterrestrial intelligence might take. The development of new techniques for searching for ancient intelligence on Earth could be directly applicable to the search for extraterrestrial intelligence. Methods for detecting technosignatures in geological records might be adapted for analyzing data from exoplanets or other celestial bodies. Future research directions. The search for ancient Earth civilizations is still in its infancy, but several promising research directions are emerging. Advances in analytical techniques, computational methods, and theoretical frameworks are opening new possibilities for investigating this question. High-resolution geochemical analysis of ancient rocks might reveal subtle signatures of ancient industrial activity. Mass spectrometry, isotope analysis, and other analytical techniques are becoming increasingly sensitive and might be able to detect traces of ancient technology that were previously undetectable. Machine learning and artificial intelligence techniques are being applied to paleontological and geological data analysis. These methods might be able to identify patterns in the fossil record or geological formations that indicate ancient intelligence. Pattern recognition algorithms might detect anomalies in the distribution of fossils, minerals, or chemical signatures that could indicate technological activity. Space-based observations of Earth might provide new perspectives on the search for ancient civilizations. High-resolution satellite imagery and spectroscopic analysis might reveal unusual geological formations or surface features that could indicate ancient modifications to the landscape. The study of Earth's deep subsurface environments might reveal evidence of ancient intelligence that has been preserved in stable geological formations. Deep drilling projects and subsurface exploration might uncover traces of ancient activity that have been protected from surface erosion and weathering. Interdisciplinary collaboration between paleontologists, geologists, archaeologists, astrobiologists, and computer scientists is essential for advancing this field. The complex nature of the search for ancient intelligence requires expertise from multiple disciplines and innovative approaches that cross traditional academic boundaries. Ethical and philosophical implications. The possibility of pre-human civilizations raises profound ethical and philosophical questions about our place in the universe and our responsibilities as a technological species. If advanced civilizations existed before humans, what happened to them? And what lessons might their fate hold for our own future? The concept of civilizational longevity becomes crucial when considering the possibility of ancient Earth civilizations. If previous technological species arose and disappeared without leaving obvious traces, it might indicate that technological civilizations tend to be unstable or short-lived. This has implications for our own long-term survival prospects. The possibility of ancient civilizations also raises questions about our uniqueness as a species. Humans often consider themselves to be the pinnacle of evolution and the first truly intelligent species on Earth. Evidence for ancient intelligence would challenge this anthropocentric view and might require us to reconsider our place in the natural world. Environmental considerations become particularly relevant when examining the possibility of ancient civilizations. If previous technological species existed and subsequently disappeared, their fate might provide insights into the long-term environmental consequences of technological development. Understanding how ancient civilizations might have affected their environment could inform our approach to current environmental challenges. The search for ancient intelligence also raises questions about the nature of intelligence itself. Human intelligence is shaped by our particular evolutionary history and biological constraints. Ancient intelligence might have taken very different forms, challenging our assumptions about what constitutes intelligence and consciousness. Conclusion. The question of whether advanced civilizations existed before humans remains open, with compelling arguments on multiple sides. While no definitive evidence for pre-human technological civilizations has been found, the vast timescales involved and the limitations of the geological and fossil records mean that such civilizations cannot be definitively ruled out. The scientific approach to this question requires rigorous methodology and careful consideration of multiple lines of evidence. The absence of obvious technological artifacts in the geological record does not necessarily prove that ancient civilizations never existed, given the poor preservation potential of most materials over millions of years. However, the lack of compelling evidence, despite extensive geological and paleontological research, suggests that if such civilizations existed, they were either very brief, very small in scale, or fundamentally different from human technological development. Several key findings emerge from this examination. First, intelligence has evolved multiple times throughout Earth's history, taking diverse forms adapted to different environments and ecological niches. From the problem-solving abilities of cephalopods to the complex social behaviors of dinosaurs, intelligence appears to be a recurring theme in evolution rather than a unique human achievement. Second, the development of intelligence appears to require specific combinations of factors, including complex nervous systems, environmental pressures that favor cognitive abilities, social structures that support learning and cultural transmission, and sufficient time for these capabilities to evolve and be refined. The particular combination that led to human technological civilization may be relatively rare, but it is not impossible that similar combinations occurred in other species throughout Earth's long history. Third, the geological and fossil records have significant limitations that constrain our ability to detect evidence of ancient intelligence. The rarity of fossilization, the poor preservation of soft tissues and organic materials, the temporal resolution of geological deposits, and the geographic sampling bias of fossil sites all contribute to an incomplete picture of ancient life. These limitations mean that brief or small-scale civilizations might exist in Earth's past without leaving detectable traces. The Silurian Hypothesis provides a valuable framework for thinking about what evidence we might expect from ancient civilizations and how long such evidence might persist. The analysis suggests that even industrial civilizations lasting thousands of years might leave surprisingly little trace in the geological record if they occurred millions of years ago. This sobering realization highlights both the challenges of detecting ancient civilizations and the fragility of our own technological legacy. The search for ancient Earth civilizations has important implications beyond mere curiosity about the past. Understanding the frequency and longevity of intelligent civilizations informs our estimates of extraterrestrial intelligence and helps us evaluate our own long-term prospects as a technological species. If intelligence is common but technological civilizations are brief, it would explain both the absence of obvious ancient technologies on Earth and the apparent absence of detectable extraterrestrial civilizations. The possibility of alternative evolutionary pathways toward intelligence opens fascinating questions about the diversity of cognitive strategies that might evolve in different environments. Marine intelligence, distributed intelligence in social insects, and potential silicon-based or quantum-based forms of cognition all suggest that intelligence might take forms very different from human cognition. Recognizing and understanding these alternatives could be crucial for both detecting ancient intelligence and communicating with extraterrestrial intelligence if it exists. Recent advances in analytical techniques, computational methods, and theoretical frameworks are opening new possibilities for investigating ancient intelligence. High-resolution geochemical analysis, machine learning approaches to pattern recognition in geological data, and interdisciplinary collaboration between multiple fields of study are creating opportunities to search for ancient technosignatures with unprecedented sensitivity and sophistication. The ethical and philosophical implications of ancient civilizations cannot be ignored. If previous technological species existed and disappeared, their fate might provide crucial insights into the challenges facing technological civilizations. Understanding the factors that determine civilizational longevity could be essential for ensuring our own long-term survival. The environmental implications are particularly relevant in our current era of anthropogenic climate change and environmental degradation. If ancient civilizations modified their environment in ways that contributed to their disappearance, these lessons could inform our approach to contemporary environmental challenges. Conversely, if ancient civilizations found sustainable ways to develop technology without devastating their environment, understanding their approaches could provide valuable guidance. The search for ancient intelligence also challenges us to think more broadly about the nature of intelligence itself. Human intelligence, while remarkable, represents only one possible solution to the challenges of survival and reproduction in a complex environment. Other forms of intelligence might be better adapted to different environments, or might have capabilities that we can barely imagine. As we continue to explore this question, several research priorities emerge. Developing more sensitive techniques for detecting ancient technosignatures in geological deposits remains crucial. This includes both improving analytical methods for detecting unusual chemical signatures and developing theoretical frameworks for predicting what signatures ancient technologies might leave. Expanding our search to previously unexplored environments could yield new insights. The deep ocean floor, subsurface environments, and extreme environments where preservation might be enhanced all represent potential repositories of evidence for ancient intelligence. Similarly, examining Earth's geological record from new perspectives, using approaches borrowed from astrobiology and SETI research, might reveal signatures that have been overlooked. Theoretical work on alternative forms of intelligence and technology remains important for guiding empirical searches. Understanding how intelligence might evolve in different environments and what forms technology might take under different constraints helps inform our search strategies and prevents us from overlooking evidence that doesn't match human technological patterns. The integration of multiple disciplines continues to be essential for progress in this field. Paleontology, geology, archaeology, astrobiology, computer science, and theoretical physics all contribute important perspectives and methodologies. The complex nature of the search for ancient intelligence requires this interdisciplinary approach and continued collaboration across traditional academic boundaries. Looking toward the future, several scenarios seem plausible. Continued research might eventually uncover compelling evidence for ancient Earth civilizations, revolutionizing our understanding of intelligence and our place in the universe. Alternatively, more thorough searches might strengthen the case that technological civilizations are extremely rare, and that humans represent a unique or nearly unique development in Earth's history. A third possibility is that ancient intelligence existed, but took forms so different from human technology that we have difficulty recognizing it as intelligence. This could include distributed biological systems, quantum-based information processing, or forms of environmental manipulation that don't leave obvious technological signatures. Recognizing such alternatives would require expanding our definitions of intelligence and technology. The question of ancient Earth civilizations ultimately reflects broader questions about the nature of intelligence, the frequency of technological development in the universe, and the long-term prospects for complex life. While definitive answers remain elusive, the search itself advances our understanding of evolution, intelligence, and our place in the cosmic story. Whether or not advanced civilizations existed before humans, the scientific investigation of this possibility provides valuable insights into the nature of intelligence, the limits of the geological record, and the challenges facing technological species. The rigorous, evidence-based approach required for this investigation exemplifies the scientific method at its best and contributes to our understanding of fundamental questions about life, intelligence, and civilization. As we face our own challenges as a technological species, the lessons learned from investigating ancient intelligence become increasingly relevant. Understanding the factors that promote the evolution of intelligence, the conditions that allow civilizations to thrive, and the potential threats that face technological species could prove crucial for ensuring our own long-term survival and success. The search for ancient Earth civilizations remains an active and evolving field of research. New discoveries, improved analytical techniques, and novel theoretical frameworks continue to shed light on this fascinating question. While the mystery may never be completely solved, the investigation itself enriches our understanding of intelligence, evolution, and the remarkable story of life on Earth. In the end, whether or not ancient civilizations existed before humans, the question itself reveals something profound about human nature. Our insatiable curiosity about our origins, our place in the universe, and the nature of intelligence itself. This curiosity drives scientific discovery and expands the boundaries of human knowledge, ensuring that the search for ancient intelligence, regardless of its ultimate conclusions, contributes to the ongoing human endeavor to understand ourselves and our universe. The implications extend far beyond academic interest. In an era when humanity faces unprecedented challenges, including climate change, environmental degradation, and the potential risks associated with advanced technology, understanding the long-term trajectory of intelligent civilizations becomes not just fascinating, but essential. The search for ancient Earth civilizations is ultimately a search for wisdom about how intelligent species can thrive over cosmic timescales. As we continue this investigation, we must remain open to possibilities while maintaining rigorous scientific standards. The extraordinary nature of the claims requires extraordinary evidence, but we must also be prepared for discoveries that challenge our fundamental assumptions about intelligence, evolution, and the history of life on Earth. The universe has surprised us before, and it will likely surprise us again. The story of intelligence on Earth is still being written, with each new discovery adding chapters to this remarkable narrative. Whether that story includes pre-human civilizations remains to be determined, but the search itself has already enriched our understanding of the complex, dynamic, and endlessly fascinating world we inhabit. As we look to the future, this investigation serves as both a window into the past and a guide for navigating the challenges that lie ahead for our own civilization.